Oh well, maybe I'll just have. I can see you anyway. I don't know why.
Oh,
Maybe.
okay, that's doesn't matter. But at least I can hear you.
Yeah, that's a shame. Oh,
Okay, next time we will do a little bit more technical stuff first. So, okay, let me just share my screen so that we can start. Share, share screen, and I'm going to share this screen. Okay, share.
yeah, I can see all that. That's good.
Okay,
I can see myself on the screen now, on the little screen.
probably will take a while for it to go through to the rest. But anyway, do you see my screen?
Yeah, yeah, I can.
Back
Yeah,
history. Yep. Okay. Let's.
You need to reverse your camera, Anthony, I think.
yeah. I don't know how to do it. I can't figure out how to make it happen.
Is the camera pointing outside?
Is it?
I can't see your camera, so I don't know.
No, it's my laptop, so it shouldn't be looking outside anyway.
But anyway, let's get started.
Yeah, yeah. Start.
Okay. Let me see how I can switch the screen here. Come on. Yeah. Okay. Let me see whether. Yep. Okay. The first light. So last time we talked about the universe after expanding. Then during the expansion, it is so hot that most of the matter are ionized, and therefore light cannot pass through. So it is opaque. Then when the temperature drops below a certain temperature, where the nucleus and the electrons can be combined. So after recombination, the amount of charged particles started to decrease and then eventually all go away, and therefore the universe becomes neutral, and at that time it becomes transparent, and the lights that come out at that time after all the redshift etc becomes the cosmic background radiation we are observing today. Up from that point onward, the universe is basically black, no light, because there's no object which will emit any light. So it is a black. So here we are good looking at how the first light come out. So just a recap, we have at the very beginning we have the quantum fluctuation, and then a Big Bang, and then inflation. After inflation, then at around 375,000 years after the Big Bang, then we see the afterglow. That is the cosmic microwave background radiation, and then it enters into the so-called dark ages. It is really dark because there's nothing providing any light. The universe basically is just filled with some hydrogen, a little bit helium, very tiny bit of lithium, and so forth. Only the first few elements. And then this is what it looks like at that particular time. There are some places a little bit hotter, there are some places a little bit cooler. The temperature difference there is very small. It is about a few 0.006% about degrees centigrade. So it's a very tiny temperature difference. But this tiny temperature difference represents some very interesting characteristics, which eventually evolve into the universe we see today. So after the combination of the electrons and the protons to form hydrogen, etc., the universe becomes transparent. The last glow, which is the cosmic microwave background radiation, and then get into the dark age. So that summarizes what I have just said. And again, we talk about why there are some minor temperature fluctuations. The main cause are some of the quantum fluctuations, some sound waves passing through the universe at that time, etc., etc. So there are minute differences, but this minute difference started to operate under gravity. Gravity attracts. So for regions which has a little bit more nucleus, a little bit more atom, it would start to attract the nearby atoms to move towards it. So there is a attraction now starting to happen. The denser areas becomes a center of attraction. So it's starting to attract. But this is about the beginning formation of the star. The star formation is a process by which a dense region, more hydrogen, started to attract other molecules towards it. So as it get combined together, the potential energy, that means the energy it comes from gravity, is collecting towards these molecules. So these molecules are accelerating towards this denser region. As it accelerates towards the denser region becomes a little bit hotter and hotter, and eventually it will light up. So that is what we shall see in a moment. I think somebody's trying to enter. Is that right? Let me see. Let me go to the wheel. No, there's no. Okay, doesn't matter. Okay, I'll continue. But in order to explain what we really observed, if it is only all the visible matter, then up to now the universe shouldn't have any star yet. There's another object, another things which is attracting the molecules much quicker than gravity, and that is what we call the dark matter. Without dark matter, the universe will evolve much slower than expected. Today, the universe has evolved about 4 to 5 times faster than simply based on gravity. So that is why they say, okay, there are something which has effects on gravity, but doesn't have effects on other things. So that is what we call dark matter. So basically,
so did they propose dark matter because their observations was that the planets or the galaxies and things weren't forming quickly enough, so
yes. Dark matters, they propose dark matters based on several things. One of the things is the speed of evolution. So that's exactly what you said. This is part of the reason, but there are more reasons than just that. But anyway, let's look at what is dark matter first. Now, dark matter can interact with matter via gravity. So it is like matter. It attracts, okay. But it's not made up of matter. How do we know that? Because if it is made up of matter, then you will have the properties of matter that which can observe. For example, it will interact with light, electromagnetic waves, electromagnetic radiations. Now, one thing we at the moment we can try to see how much hydrogen is in the space, etc., is by looking at the atomic spectrum. So if light passes through a hydrogen, for example, then the particular frequency which will trigger the hydrogen's electron to jump from one orbit to another orbit will be absorbed. So we will see an absorption spectrum. And then as the electrons return to its ground state, it will emit the radiation, but will probably emit in other directions, not exactly the same direction as coming to us. And therefore, we should be able to observe the dark matter's spectrums, if there's any. But we can't. We cannot observe dark matter. So it is not matter. If it is matter like hydrogen, whatever elements, it will be able to show its atomic spectrum. But dark matter doesn't show any atomic spectrum, and therefore we know that it doesn't interact with electromagnetic radiations.
So it absorbs, say, visible light, but it can't emit anything.
No. If it absorbs emission, we can still see it, because that means there will be some light we can't see.
Yeah.
But it's not. It doesn't interact with light. So light just pass it right through.
Oh.
But no.
But it is absorbing some radiation, some wavelength.
No, it doesn't. Dark matter doesn't absorb anything. So that is the interesting thing. It's called dark because it doesn't absorb nor emit. So we don't know that. It seems like passing through, but
yeah.
But again, say passing through is not exactly correct, because it has gravitational effects, and therefore it will be like gravitational lensing. Now let me explain this. According to Einstein, we have a very massive mass, or a very large gravitational attraction area in one spot in space. For example, there's a very large mass accumulated there. Okay, there's a large attraction. Then when light passing through, it will bend because of this gravitational force. So we know that in some area of our universe, when we look at it, we see some objects which look like coming through a lens. That if we, for example, if we are holding up a lens in sky, okay, and looking at, for example, the background through the lens and next to the lens, okay, if we are seeing through the lens, then the object in the lens is a little bit magnified or bent, whereas the area outside the lens doesn't. So when we look at the sky, we can see this so-called lensing effects. If there's a lens in the universe somewhere, dark matter behaves like a gravitational lens. It bends light because it has gravity, so it bends light. But if it bends light, then the light passing through it is either be absorbed or do something, but it doesn't. Light still pass through, as if it has no effect on light. Yes, it's weird. That's why it's called dark matter.
But if it interacts with gravity, why doesn't it interact with itself and form sort of dark planets?
Yeah, it interacts with itself, but what it forms we don't know. But it is this extra gravity due to the dark matter increases the speed of the universe attracting each other. Because let's say we have a weak, many weak magnets distributed on the table surface. The magnets are attracting each other, so the magnets are moving towards each other slowly. But among some of the places there's a big magnet there. So all the small magnets tend to migrate towards the bigger magnets, because the bigger magnet produces a large attractional force. Now, that big magnet, unfortunately, we can't see. We know that there is something attracting all the small magnets towards it, but we can't see it. It doesn't interact with light. Now remember, when we do astronomy or cosmology, the only instrument we have is light. It is the light coming from different objects that we observe, and then from the light we deduce the properties of the objects. When this dark matter doesn't produce any light or interact with light, then we can't study it. So it's called dark matter. We don't know. It's weird. It's very, very weird. And therefore, and more importantly, it seems that its gravitational effect is at least 4 to 5 times larger than what we observe from the pure matter. So we say it is about 5 times as many dark matters as matter. Because its gravity effect is about 5 times larger. That means it speeds up the whole universe at least by 5 times. But actually, it's in fact it's more than that because it is not a linear relationship. But anyway.
So if it's doing that though, then it must have mass of some sort.
It interacts with mass. Yes.
Interacts with it, but doesn't have a mass itself.
We don't know.
Oh, I see. Okay.
We do not know because we can't. Again, we are not able to travel to there, get the sample, and then take it back to Earth to study. We can't. So we can only depends on all the lights that come around it, through it, etc., to try to understand it. So basically that means our instrument of investigation is very much limited. We are only limited. Our only instrument is light, nothing else. We cannot touch it. We cannot go to it. Whatever, because it is just too far away. Okay, moving on. Dark matter plays a very crucial role in. Come on, where? My screen moved. Hey, where's my cursor? Go back to my screen first. Yeah, back. Okay, dark matter plays a very crucial role in structure formation because it can feel gravity. Now, there is something called James instability that I will go through a little bit later on. But we have talked about how do we know that because it will form so-called halos. For example, during daytime, when you look at some bright object on the sky, for example, at the sun, we will see some color around the sun. That's called halos. Or if you are doing photography, then you have the shape of your diaphragm at light spots on your photograph. What do they call? They call bogus, something like that. The little circle of the light. Now that effect is due to a light passing through a refractive object. For example, light pass through a lens, then you form these halos. So we can see the halos, and therefore we know that there are something which will bend the light, and that bending is due to gravity, but we can't see what is that bending. Okay, now let's go to the James instability first. Now, James instability basically says when all the molecules, hydrogen, etc., move towards a denser region, then it will form a gas pressure because, like any gas, it will have a pressure among each other. But the gas is being held together by gravity. So James is a man. His surname is James, something James. He proposed, it is an Englishman. He noticed that under certain conditions, when the gas pressure and the gravity balance out, then it will be stable. Any other conditions, then it is not stable. Basically meaning when the gas is being held together by gravity, then it is stable. But that is very sensitive to both the gravity itself and the temperature. If the temperature is high, that means the gas is running out faster, so the gas cannot collapse onto itself. But if the gravity is larger than the temperature, then it will still attract the gas to come closer and closer. until its temperature is balanced out by the gravity. Then it will be stable. Okay, that's pretty easy to understand. The problem is, at some temperature, it is no longer just the gas pressure. There are some other effects that might happen, like temperature so hot that it becomes the molecules becomes ionized, becomes a opaque plasma, and then under plasma conditions, then you will subject to electromagnetic effects on top of the simple ideal gas effects, and therefore it will collapse. So James instability actually describes a condition that control whether a lump of gas will collapse onto itself. That means it will attract, and becomes so small, then it ignites and started the thermonuclear fusion. Okay, this diagram we should look at from you will look at from left to right, then it is from current to future. If we look from the right from left, then it's looking from the beginning of the universe to today. Now this is represented by distance, because we know that for very large, very distant object, it will take time to come to us. So the further we look, the further in the past we are looking. Whatever that come to us from, say, 1 light year away, that means the light left that place 1 year ago and then it reaches us here today. If it is 3 light years away, then the light will have left 3 years ago and then it arrived at our place today. So that is how the light and time are related. And this diagram is a log scale. It's not a linear scale. So equal distance is only equal in the number of zeros. Okay, so on the very right, on the right side, is the beginning of the universe. And then we see a grow lights, the band. Let me see here. About here is when the universe now have recombined, and then grow out that particular light. The cosmic background radiation is emitted around this time, and then the universe enter into this dark age here. The little bit dark ages, and then the universe started to collapse together. So some regions are attracting each other and then form all these tubular structures. And these tubular structures, all this region here, is explained by dark matter. The dark matter, using dark matter into a computer model, will be able to for us to draw something similar to this one, to this region. There are some regions lighting up. This lighting up might be the early formation of stars, and that stars, because it formed so early, so it's probably very short light. The lifespan is very short, and eventually all these will lump together and form early galaxies and stars. So during this region, it is still bright a little bit. So we just have come out from the cosmic background radiation from this region here, cross the dark region. After the dark ages, then it comes with all these recombinations, reionizations, and so forth. And then I want to jump to this part here. All these wonderful little filament-like structures has to be explained by dark energy, dark matter, and people have done simulation on it. So, but again, this is very highly mathematical. So we are going to skip over this part, and then we'll look at how these structures are formed here in this region. Okay, let's move on. Formation of galaxy. Galaxy is basically a number of stars combined together. In between them, there are some gas, etc. The word galaxy original means Milky, referring to our own galaxy, Milky Way. So a galaxy might have around several hundred millions of stars to 100 trillions of stars. So the number of stars is highly variable, as well as large number of stars. In the middle of the galaxy, there is a very large black hole. This very large black holes that hold all these stars together, because all these stars are matter. This matter will be attracted by gravity, and why they are stick together is because there's a big magnet attracting them. So they are all attracted by this big magnet, and therefore it is formed into this huge galaxy. The galaxy itself is very large. Our own galaxy, our own sun is on the edge of our own galaxy, and our galaxy is part of a larger structure. Our galaxy's middle is called this thing. It has about 4 million times the mass of our star. And there are different estimations about how many galaxies in the universe. Some say it is about 200 billion, to some even suggested 2 trillion. So that the number of galaxies there is again a large variety. We really haven't really get a grip of how many are there. And in terms of the size of the galaxy, is approximately 3,000 to 300,000 light year across, with separations between them talking about millions of light years. So galaxy, why it forms like that with such a large separation is because of dark matter. Without dark matter, it will not form in this way. The space between galaxy is the intergalactic space. Then it has almost nothing there. It's about 1 atom per cubic meter. But in the center of the galaxy, or in the center of any star, we are talking about 10 to the power 40 something molecules per cubic meter. So there's a huge difference. This large difference all started at the very beginning with minute difference, very small difference at the very beginning. After the Big Bang, the cosmic microwave background radiation so as that the difference in density is only a few percentage. Oh no, even less than a few percent. Is a few 100,000th of a percent. It's very small. But now the difference is huge because of this gravity force and the dark matter attracting all the gas together to form galaxy and stars. Now this is a picture of our Milky Way. Take a location in Chile in South America. So in Australia here at night, on a good night, we can see this galaxy ourselves here. When I was in Hong Kong, I wasn't able to see that because Hong Kong has so much light pollution. But here, in Melbourne here, at a good night, we can actually see part of this Milky Way. So this is the Milky Way. We are somewhere on the edge, and this part is the middle of the Milky Way is like almost a plate, a dish. It is pretty thin. Of course, a little bit thicker in the middle, but will be thin out on the edge. And this is the middle. Why it is in an arc? Because we are taking it from Earth, and then because of the angle. Okay, let's move on. We'll look at the star evolution. We will look at this in more detail next time, but we will look at a little bit of star evolution. The star evolution is the process by which stars change over the course of time, depending on the mass of the star. Its lifetime range from a few million years to trillions of years, which will outlast the age of the universe, probably longer than life. Now, we don't know what it will be the age of the universe at the moment yet, because the universe might expand forever. At the moment, the universe is about 13.6 billion years old. But for some lighter stars, the expected lifespan is trillions of years, so it will outlast whatever we observe. But how that evolved, we don't know yet. Okay, we only know they past 13.6 billion years. But all these estimate of them having trillions of light years old is based on calculations. All stars are formed by collapsing clouds of gas and dust, and that process took millions of years until it settled into a state of equilibrium. Again, that comes back to the James instability. As the gas is attracting towards a center, it gets hotter and hotter, and eventually, if the temperature reaches the temperature at which thermonuclear fusion can happen, then the star will start burning hydrogen at that stage and becomes a star. Star evolution is the gravitational collapse of a giant molecular cloud, a large amount of molecules. The typical cloud size is 100 light years. So you can imagine a very large distance. These molecules are moving towards the center and then heating up. And it can contain up to 6 million solar mass. So during that time, some of them will start light up before the others, and it forms a little cluster of stars.
And what are those molecules that are collapsing to form stars? Are they basic stuff like helium?
They are basic stuff like hydrogen, mostly. Okay. The universe is started with only hydrogen and helium, so they are all hydrogens. Yeah. Not much other molecules, because the other molecules have to be formed in the star themselves, so it will come out a little bit later on. Okay, so I put those stars about the mass of our sun, which is denoted by the M with a circle dots underneath it. That is the symbol for the mass of our sun. So there are different sizes. The size range is huge. Some star is much smaller than our sun, but there are some which is very, very much larger than our sun. So typical, our sun is very typical. So there are, the normal size is our sun, to put it that way. For the smaller ones, 0.08, so about 8% the mass of our sun, it will not hot enough to reach the temperature for fusion of hydrogen to form helium, because it's just simply not hot enough. So it will shown as a hot amount of gas. So it's called brown dwarfs. Dwarfs is small. It is brown because it's not very hot. So it is a brown dwarfs. And this kind of brown dwarfs has a very, very long life cycle. It is talking about hundreds of billion years lifespan, because they are burning so slow. And some of them might feel some tritium, but not as much as ours. So the temperature to burn tritium needs about 13 mass of our Jupiter. Then it will, so a little bit about around 0.015 of our sun will be able to burn a little bit of tritium, but not much. In terms of, and therefore from the classification point of view, anything below the 13 Jupiter mass is known as the sub-brown dwarfs. Okay, the main sequence, this is where we are interested, and then we will spend a bit more time on this main sequence next time. In this main sequence, then, when the core temperature reaches about 10 million degrees, then there are a number of participants. How come I can't get them in? There is a lot of people waiting and can't get in. Admit, they have been waiting for a long time. I'm sorry, guys. I didn't see you coming in. Sorry. I don't know why it doesn't show up here at the very beginning for me to get people in. But anyway, I'm sorry about that. I have been streaming this online, and therefore I will be able to give you the URL to watch it online later on. So sorry about that. I'm now almost finished.
Okay, I can hear you.
Okay, sorry. Next time.
Can you hear me?
Yes, I can hear you.
Oh,
And,
good, good.
and the other people should be able to hear you as well.
Good. Okay. Good to
Okay.
be along and good on this, Albert.
Sorry to let you in so late, because I didn't realize that there are people waiting.
I was a little bit late myself. I was been painting outside. And
Yeah,
just
I
finished.
know. You mentioned suddenly my screen flashes and say there are 6 people waiting.
Yeah.
I'm sorry I didn't let everybody in earlier. Anyway.
No problem. I have something to eat and I'm sorting something out.
Okay,
I'm yours when you're ready.
we almost finished.
Yeah, that's all right. Well, I'll be on for the China.
Yeah, okay.
I'll leave. If you're almost finished, I'll leave now.
No, you stay here. You stay here first, and then I will say when to leave, and then when to enter into the next meeting. So let's stay here for the time being. Let me finish this thing first. Okay, it's almost finished. Can you see the screen saying a main sequence? Okay.
Yes.
Okay. Now we are talking.
Albert, can you hear me?
Yes. Another person in. Sorry, Jack.
I've finally got it working. Thank you.
Well, as I said, I didn't know there are people waiting outside in the meeting room. I don't know. Can they? Yeah, I will look at the settings whether they can allow automatic admission. Looks like people have been waiting.
Albert, I think you can.
Okay, I will try. I will do the settings, because I'm using the default settings. To me, Zoom is very much my first time.
Yeah, same here.
Okay, so no problem. We will get used to it later on.
We'll learn.
Yeah, we will all learn. But anyway, in case you want to catch up with this, the current what I have been talking about is now on live, and there are people watching online at the moment.
Okay.
So let me see how many people are actually watching at the moment. Let me see whether I can see the number. Okay, there are 10 concurrent viewers at the moment.
Pretty good.
Okay, well anyway,
Yeah.
let me continue with this.
All ears.
Yeah. We are talking about formation of stars. Basically, very quickly recap is that the universe started almost homogeneous with very minute temperature difference. This minute temperature difference means some area that's a little bit more dense and some area that's a little bit less dense. Under the action of gravity, with the help of dark matter, these denser regions started to attract the molecules from the nearby less dense regions. So as the molecules move towards these denser regions, then the denser regions becomes hotter and hotter. If the temperature there is hot enough at around 10 million degrees Kelvin, then thermonuclear fusion can happen. Of course, how hot it can come depends on the mass. The heavier, that means the more molecules sticking together in the region, heavier, then it will reach that temperature much earlier because there are more gas coming in, more energy, and therefore it becomes hotter. And therefore, at higher temperature, it will fuse much faster. The lifetime will be shorter. If the weight is smaller than 0. That means the more molecules sticking together in the region, heavier, then you will reach that temperature much earlier. Wait, why I am hearing myself? Therefore, it becomes hotter, and therefore, at higher temperature, it will fuse much faster. The lifetime will be. Okay, so with is smaller than 0. With that in mind, that means we are looking at the internal reactions inside the star next time. When the light when the mass is hot enough, then it will start thermonuclear fusion. When it starts thermonuclear fusion, then it is the beginning of the life cycle of the star. And again, as I said, the heavier the star, the shorter its lifespan. The lighter the star, the longer its lifespan. For our sun, the lifespan is approximately 10 billion years. About 10 billion years. Our star is now at its mid-age. We are about half through our sun's lifespan. Okay, this is a usual diagram to represent all these stars. Every dot on the right-hand side diagram represents a typical star. And the vertical axis is how bright it is, the brightness. And the horizontal axis is its color. And this is plotted using different stars from the sky. We see that all the stars mainly are located in the middle line. This line here, the middle line here. So that's called the main sequence. That's the main sequence. Our sun is approximately our sun is approximately here. This is the region of our sun. So our sun is very typical. Okay, sorry. Okay, this is the end of the presentation today.
Albert, I think Andrew's got his microphone on. I think that's where the interference is coming from.
Okay, so I now I can actually mute everybody because this is the first time. So let me just stop sharing. Hi. Now let's get a little bit of organization work. When you come in, should I automatically mute your microphones as a default?
Yes.
And then if you want to speak,
Yes.
then you might have
Yes.
to go to your screen and raise your hand so that I can unmute you.
Yep, like that. Yep.
Okay, and
Good.
that's okay. That's something I will try to change next time. And the second thing is that I will try to allow automatic admission. Because this time I see a number of people you waiting outside, but I haven't admit you because I don't know you were waiting.
Yeah.
So I will try to set up automatic admission next time. And the third thing is any other suggestion?
Hi, Albert.
Yes. How are you?
Yeah, fine, thank you.
Yeah.
I've been waiting for so long, and then on the laptop, and I couldn't get in.
Yeah, because I didn't allow automatic admission. So I didn't know that it needs me to admit everybody. I'm the host here, so I supposed to. So that's why I'm saying that next time I will allow automatic admission if it allows it, so that people doesn't have to wait outside of this conference area.
Because just from your email, you are saying that it's already automatically allow for the video and speaker.
Yeah, but this is new to me, so that's the reason why I mess up.
Okay.
And do you need password to come in?
Yes.
Yeah.
Yeah. Okay. No.
Yeah, we use all password.
Yes.
Some yes, some no. So
You see, for the Apple, I couldn't open. But for the mobile phone, I don't know. It's just automatically coming out.
Oh, so again, that is the Zoom's problem because I didn't. It is not my software, so I'm using somebody's software. So I have to see how that works. But anyway, and we will try that again next week
Yes.
at 12. Hopefully, a little bit better than today.
Yes.
And how about the 1 o'clock one, the China today?
Yeah, China today 1 o'clock. So I'm going to finish this meeting and then start the other meeting.
Yes.
Yes, you will continue using this YouTube or?
I will continue using the next YouTube video. So this video will stop about here, and then we will have another video for China today. And again, the information I will send out the links to after the China today to everybody so that you can watch what had happened before you come in or before I allow you to come in. So
Albert?
yeah, yes,
Yeah. Cyril here. I got in all right. I came in through Zoom first.
yeah.
And then it gave me the screen to put in your ID and your password.
Okay,
It worked fine. And I tried that last night. I knew that I could use your link and that information. So on your link, if you go down it gives the ID and the password.
Yeah.
You mentioned it in addition yourself. And I've been trying this for a couple of weeks for another entity, and I had trouble with my iPad on getting it to recognise things and knowing fully what I had to do. But I solved it all yesterday.
good.
And I could do a test. You could do a self-test on it. And tomorrow morning, 8 o'clock our time, but some other time in the US, I'm doing a live a live experience with it, where
Okay.
they take you through and show you a lot of the controls. I've done a few smaller things where it's just someone talking, but the other one is two-way tomorrow.
Yep.
So there's different options you have. Anyone who's not sure of it and wants to find out more on the Zoom site.
Yeah.
So
I
find
need
that
to
quite helpful.
I think I will need to take a course on the Zoom side as well.
Yeah.
Yeah.
But with the iPad, I had to have Google loaded and do shortcuts on it so it would connect with Zoom.
Okay.
It doesn't open in Safari, so there might be technical things with people on different types of machines. Yep.
Okay.
But it's working well. I've got a full picture of you there now.
Thank you.
It's really good.